in section 12.4, we're going to use polar coordinates to help us do some double integrals. And well, it'll help. Let me just go right to the formula here, and then I'll talk about that formula a little bit. So first of all, though, before we get there, you recall that in polar coordinates, r squared equals x squared plus y squared, x equals r cosine theta, y equals r sine theta, and you know you have your standard right triangle there with a radius coming out of the origin at some angle theta, measured from the positive x-axis, and so you know you recall that, I'm sure. This is a polar rectangle, okay, in figure 3. So with polar coordinates, your region D or region R, so the book will use region D sometimes it'll use region R, but you see, you have, like in a polar rectangle, you have a region R that goes from one angle to another angle, theta equals alpha to theta equals beta. And then you have two radii, r equals A and r equals B. And that delineates a polar rectangle, okay? So if we could, I mean, if we could, for instance, take a region R, and break it up into a bunch of polar rectangles and find the well, what we need is an expression for the dA in the double integral. Let me clarify this. So like in double integral, so far what you've learned is this. You know, you have a double integral. Okay, this is the standard notation for a double integral. Okay, and the dA right now can be what? The dA can be what are our choices based on what we learned in sections 12.2 and 12.3? So you know, if you think of delta A in this case is a piece of area where you have a delta X base and a delta Y height. Okay, that's a unit of area. So dA would be what? We have two choices. dA could be D something, or D something, D something. What's going to go here? That's right. You could have dy dx, or you could have dx dy. And these are units of area. Okay. And that's if you're using rectangular coordinates. But what we want to do now is we want to start using polar coordinates. Well, for polar coordinates, you know, well, let's take a look at what the counterpart would be for polar coordinates. Trying to think, I mean, I can always, well, I mean, for polar coordinates, let me just try to keep them both in the same window here. For polar coordinates, you're going to have a double integral over some region R, And f is now is a function of r cosine theta and r sine theta. Because with polar coordinates, x is equal to r cosine theta. Y is equal to r sine theta. And then you got the dA, okay, your differential for area. But the dA is not going to be it's not going to be dy dx or dx dy, because those are used for rectangular coordinates. The dA for polar coordinates is going to be, turns out, r dr d theta. That's going to be for polar coordinates. dA is r dr d theta. Now let me show you why. Well, let me go to the formula in the book, and then I'll try to justify this for you. Okay. So keep in mind, remember when we did rectangular coordinates, the dA, think of delta A, base times height is delta x times delta y. So you could have dy dx or dx dy. Okay. If we now go to the book here and go down a little bit, here's for a double integral in polar coordinates. You're going to go for a radius will go from A to B, and theta will go from theta equals alpha to theta equals beta. But why are we getting r dr d theta? Why is that? Well, if we go to the next page, you see in figure 5, they show in figure 5 here a piece of area, right? A dA, a piece of area. And the side of that little, it isn't that polar rectangle. The side is the dr, and I'm going to say this the right way. Let me go to the whiteboard. Hold on. Whoops. Okay, so you have with polar coordinates this here is the dA, right? And you have here, I want to say this the right way. Okay, so if you had like radius equals B here and radius equals A here, that's going to, in terms of a polar graph, that generates a circle, right? So the polar rectangle is generated by having two concentric circles. Okay, but you're just looking at from the origin, of course, but you're just looking at a part of them. Now, what part of them are you looking at? You're looking at from here to here and from here to here. Okay, so this little change here is d theta, because you need a change. You need like I want to say this the right way. This ray here, this is a ray. That, for instance, might have theta equals, I want to try not to use the exact letters in the book, but maybe theta equals L. And then this ray here might have theta equals, I want to be careful here. Hold on here. Okay, maybe I'll call it theta equals 01 and theta equals 02. But the point is, those are rays, and the difference in those angles is d theta. So if we want to find this dA here, this polar area of this polar rectangle, I think about, I mean, this is sort of crude, okay, what I'm telling you, but this here, this distance here is dr. Okay, it's dr, which is approximately delta r. It's like your base. On the other hand, this distance here, well, no, dr is like your height of the rectangle. Okay, and this this distance here, from here to here, that distance would be equal to r d theta. Okay, that would be equal to r d theta. I mean, let's just call. I mean, if this distance here, let me just draw it in here. This distance here is just a distance of r. Then this distance here would be r d theta. Okay, so it has to do with circumference, right? The circumference of a full circle is r times 2 pi, right? Because a full circle, this is like your d theta, right? For a full circle, 2 pi. So circumference is r times 2 pi, or 2 pi r. That's for an entire circle. Well, you just have a piece of the circle, and so that is going to equal r, just like this was r, times d theta. Okay, and so if you take the dr as your height and the r d theta as your base, you get r dr d theta. That's like taking r d theta and multiplying it by dr. And that's why you get the r dr d theta as your unit of your dA. Okay, and they mention that in the book. What I just explained here, okay, is what they talk about right here. I just gave a little more detail for you. Okay, does that maybe give me a thumbs up if you're okay with that? Okay, Charles is good. Ellie's good. Excellent, excellent. All right, well then let's go ahead and look at a few examples here. Okay, and I know nobody's looking at their exam now because I deactivated, but I'll activate it after class. I just don't, I want everybody to be participating. I'm very happy I have, 6 out of 12 people offering help participating, but I want 12 out of 12 participating if possible, okay? All right, let me go ahead here. Okay, let's do an example here. Let's do an example. Let me give you a moment to copy. Okay, so we want to find the volume of the solid bounded by the plane z equals 0 and the paraboloid z equals 1 minus x squared minus y squared. Okay, so is this paraboloid, is it like a paraboloid that goes up, or is it a paraboloid that goes down? What do you think? That's right, Juliana. It goes down. What's the largest value of the paraboloid? What's the high point of the paraboloid? What's the high z value? That's right, Charles. Z equals 1. Okay, so remember now what we have to do. Okay. You know, the volume problems are important because they help you understand. They help you with your three-dimensional thinking, which is important. Okay, so the problems I assign in the homework, I choose them carefully. Okay, so what do we need here? We need, for any integral, double integral, we need some function of x and y. Okay, we need a dA, and we need a region D. Now, if we're going to use polar coordinates, okay, well, we need a region D. We'll call it region R. Okay, we need a function of r cosine theta, r sine theta, and then our dA. Of course, dA for rectangular coordinates is dy dx or dx dy. But if we're going to do polar coordinates, dA is going to be just what? R dr d theta. Okay, that's the dA. R dr d theta. So in order to do this problem, what's the surface that's bounding this solid above? What surface is bounding this solid above? A solid has to be completely bounded, you know. So we know, well, we got the plane z equals 0 and the paraboloid. That's right, Charles. The paraboloid is bounding this solid above. The plane z equals 0 is bounding this solid below. And the plane z equals 0, by the way, is what coordinate plane? What coordinate plane is the plane z equals 0? Good, the xy plane. Very good, very good. So, what do we need to do what do we absolutely, if we're gonna use polar coordinates, and that'll be better. Okay, here. We're going to use polar coordinates. What do we need to find? What do we need to find? Look at the polar coordinate thing. Look at the formula here. What do we need to find in order to compute our double integral? What don't we know? I know I'm going to be having r dr d theta as my unit of, or my choice of integration. What here don't I know to compute this integral? Well, okay, Charles, what we're going to do, we're going to just substitute in, like for x, we're going to substitute in r cosine theta. And for y, we're going to substitute in y r sine theta. So this function here, we're going to know that. We're going to be able to write that out. Okay, so Ellie says I don't know the endpoints. And the reason I don't know that's right, I don't know the endpoints because I don't know my region of integration. I don't know my region of integration. How am I going to be able to determine my region R of integration? I have a solid. I have a solid that exists over some region in the xy plane. It exists over some region in the xy plane. How would I find that region? Well, so Charles is basically saying make use of the plane z equals 0 and the plane and the paraboloid. What happens to the paraboloid? When the paraboloid goes downward, eventually it's going to reach that xy plane, right? So what's very important to determine between the paraboloid that goes downward and the xy plane? The intersection. Intersection's everything, class. Good, Ellie. Intersection's everything. So we're going to do that. Here we go. So, all right. Here is a picture of my paraboloid going downward to the plane z equals 0. Note where the paraboloid intersects the plane z equals 0. That means then that where that intersection is, 0 has to equal 1 minus x squared minus y squared, or x squared plus y squared equals 1. So my region D is this circle here. My region D is this circle centered at the origin with radius 1. Okay? Now what I do here, and I'm trying to give you as much context as I can give, if we were to use Cartesian coordinates, or those are also known, class, as rectangular coordinates. Okay. If I were to use rectangular coordinates, this would be the volume. This would be the volume. I have a function here on the bottom, z equals -1 square root of 1 minus x squared, and I have a function here on the top. So a circle A circle, if you take a circle, x squared plus y squared equals 1, and okay, then y squared is 1 minus x squared. That means y equals plus or minus the square root of 1 minus x squared. So you have to create a circle requires putting two functions together. The positive square root of 1 minus x squared and the negative square root of 1 minus x squared. Okay, you put those two together and you'll create a circle. And so the volume that we're looking for in Cartesian coordinates is given as this double integral. The problem is this double integral is not easy to evaluate. So we're going to use polar coordinates instead. Let me give you a moment to catch up here. Tino, how are you doing? Are you comfortable with this material? I'm just, while you're copying, I'm just chatting to a few people here. Okay, Kino, are you there? Okay, Marwan, how about you? Are you, how are you feeling about this material? Marwan, can you hear me? Okay. Hyunu, how about you? Hyunu, are you all right? Okay, all right, all right. All right. Gordon, how are you feeling with it? How are you doing with it? All right. Okay. Well, all right. I'll go. I'll take my time here. Nothing too bad. All right. Are there any questions on this right here? This triple integral. A double integral, sorry. Double integral, right. Right. I meant double, Charles. Are you understanding the principle here? Right, that's right. I mean, is anybody uncomfortable? We will, yes, Malik. We'll get to triple integrals on Wednesday. Please tell me now, if you're not understanding. Please let me know. Everybody's okay on how I got these limits? Well, you know what? So normally, if you're dealing with, it really depends on the integral. Normally, if the integral involves a circle, oftentimes it's easier to use polar coordinates. So the paraboloid has z equals 1 minus x squared minus y squared. The minus x squared, the minus x squared minus y squared could be written as minus r squared. And that's a little easier. So it really depends on the integral. This integral here is not easy to evaluate. Okay? So what we're going to do is we're going to use polar coordinates instead. So what I do is this here, 1 minus x squared minus y squared is the same as 1 minus r squared. And then I use r d theta. And then now my limits on the radius are 0 to 1. So above there, I have a circle of radius 1. All the points inside that circle, all the polar coordinates inside that circle would have a radius from 0 to 1. And all the points inside this circle here would have angles that vary between 0 and 2 pi. So which integral looks easier to you? Kino, which integral looks easier to you? Integral 1 or integral 2? I'm doing this. All right, Ian thinks integral 2. Marwan, what do you think? Integral 1 or integral 2? Which looks easier? Or double integral 1 or double integral 2? All right, so see, I'm Dr. Duty's using his spy skills to find out who's like on the roster there in the room, but where are they? All right, maybe they're in the bathroom. We'll see. We'll check back a little later here. I hope they didn't fall in. Is that good calculus humor, everybody? All right. We like everybody in here. I like Marwan and Kino. I like everybody, but I want everybody here. All right. So we're here now. We're on the second double integral. Let's integrate it. Let's go. Are there any questions on how I got the limits for r and the limits for theta? Okay, well, let's move on then. Here we go. So I'm going to iterate the integral. Okay, so r dr is there. I'll distribute the r into the 1 and into the r squared. And, you just work it out. And in the end, you're going to get pi over 2. So if you're designing a bowl that has the shape of that upside down paraboloid, and it has that solid shape, that's the volume of the bowl. That's the exact volume. Okay. Please let me know if you have any questions. All right, are we ready to move on to the next example? Okay, thank you, Charles. Thank you, Ian. Thank you, Juliana. Thank you, Ellie. Thank you, Madeline. Who else is here? Give me a thumbs up, please. Who else is here? Hunu's here. Gordon's here. Thank you. I'm going to start doing this. I'm going to start doing this. Because you know, I think it's the right thing to do. You know. All right. Let's go on here. No. All right. A new example. Okay, take a moment to copy it down. So we want to find a volume of a solid above this cone, and this is the top part of the cone. Okay. So remember the cone, as always, sort of the standard cone you see in the problems is, you know, like x squared over 1 plus y squared over 1 equals z over 1. That's cone. Remember from section 9.6, A, B, C, the standard form of a cone. That meets the requirement. And then if you take the square root of both sides, you get the positive. Well, I mean the actual cone itself is z equals plus or minus square root of x squared plus y squared. And that'll get you both the top and bottom parts of the cone, right? Coming from the origin there. But you're only going to get the top part of the cone here because you have a plus here. And that's a plus, right? So what you have is you have a cone. You have a cone. Okay, coming out from the origin. And then the cone gets stopped by the sphere. So this is maybe not a perfectly great picture, but it's going to be, as Charles says, the shape of an ice cream cone. So what we need, of course, is, again, here we are, double integral f of r cosine theta, r sine theta, times dr d theta over a region R. One moment. Now, what is critical to find? What is critical to find? To be able to compute this volume, Right. Good, Juliana. Excellent. The points of intersection between the cone and the sphere. Okay, so we have to find those points. Now, the cone and the sphere, what do you think, what's it going to be, the intersection? What's the intersection going to look like between the cone and the sphere? A circle. That's right, Ellie. It's going to be a circle. Okay, so let's go and find out that circle. Okay, so clearly I can take this z and substitute it in right there in the second equation, and that's what we're going to do. Now this problem's a little more involved than the first one, and you'll see why. So the cone and the sphere intersect in the circle x squared plus y squared equals a half. That's a circle of radius 1 over root 2, and it's centered at the origin there. Let me give you a moment to catch up here, okay? Let me know if you have any questions. Sorry, I didn't know my volume was off. Let me try this again. So um, here what I've done is I've put in I've outlined the ice cream cone. Okay, the ice cream cone has a surface on top, which I shaded in blue. Okay, and then it has a surface below, which I shaded in red. So the ice cream cone, unlike the paraboloid had, like the previous example, had a top surface which was the paraboloid, but then the bottom of the surface of the paraboloid was just the XY plane. But now we have a surface on top and a surface on the bottom, neither of which is the XY plane. The surface on top is part of what surface? The surface on top comes from what? The sphere or the cone? So this surface here, look at the picture. This surface here on top, that surface is part of, is it part of the cone or is it part of the sphere? That's what I mean. It's part of the sphere. That's right. That's right, James. Or Ian. That's right. Now the surface on the bottom, is that part, which I have here in red, is that part of the sphere or part of the cone? The surface in red on the bottom. That's part of the cone, Ellie. That's right. The surface on the bottom, so the ice cream cone, this surface on the bottom here, okay, does that surface on the bottom come from the, is that part of the sphere or part of the cone? Well, it's part of the cone. So you see, Julian, are you okay with that? Okay, excellent. So how are we going to determine the volume of this ice cream cone? Well, what we can do is we can take the difference of two volumes. That's what I got here. This is the difference of two. This here is the difference of two volumes. Now the x squared plus y squared less than or equal to a half, this part here, that's going to be my region based on the fact that region, okay, in the xy plane, of course, if you take the intersection between the sphere and the cone and project that intersection down in the xy plane, that gives me my region D. And that region can be described as x squared plus y squared less than or equal to a half. Okay? But now what I want to do is I want to show you why the volume of the ice cream cone can be written as the difference of two volumes. So the first volume, what does this first volume here represent? That's going to be this volume here. Well, it's this volume here is this volume here is the volume of a bullet. That volume is the volume of a bullet. This double integral, the double integral, where the function is the square root of 1 minus x squared minus y squared, that's the top part of the sphere. And if you take the top part of the sphere and restrict it over this region, x squared plus y squared less than or equal to a half, if you restrict it, that volume is going to be the volume of a bullet. Okay, because what the top part of the bullet is the sphere, and then the bottom part of the bullet is in the xy is that circle in the xy plane. Okay, so I meant that this function comes from the sphere, but now this second double integral here, this second double integral, okay, right here, this one, okay, that's going to be the volume represented right here in the shaded area. That's taking the cone and looking at the volume beneath the cone over that circular region in the xy plane. So I've shaded in for the first volume, the bullet, the volume of the bullet, and right here. And then in the second volume, I've shaded in the volume below the cone. Well, you see that if you take the volume of the bullet and subtract the volume underneath the cone, that you're going to get the ice cream cone? Do you see that? The difference of those two double integrals gives you the volume of the ice cream cone. Is that okay? You have to stop me if you're uncomfortable. Okay, Juliana says that makes sense. Good, good. Ellie's good with that. Charles is good. Excellent. I'm taking my time here. I'm taking my time. Okay, Madeline says it makes sense. Good, good, good. Well, so now, you notice I'm not doing too much at once here. Well, okay, well, that's all right, Ian, one step at a time. I'm not worried about whether I'm going to integrate with respect to region X or whether I'm going to integrate with respect to rectangular coordinates or polar coordinates right now. You notice I have the dA here. I'm just setting up how I'm going to do the problem. Now that I've set up how I'm going to do the problem, now that I got my setup right here, okay, now I'm going to decide, well, should I integrate with respect to polar coordinates or rectangular coordinates? Well, if I stick to rectangular coordinates, I'm going to have square roots involved. Square roots are difficult to deal with. Remember the Lagrange multipliers problems when you had to find the minimum distance? What did we do with the and so the function to minimize is the distance formula. What do we do with the distance formula? We don't minimize the distance formula. We minimize the distance formula what? We minimize the distance formula squared. So same kind of principle here. That's right. I'm gonna pick what variables I'm going to use to make my life easier. And I think polar coordinates are going to be easier. So let's go to the next page. Now, incidentally, if I'm subtracting two double integrals here, I ought to be able to combine the two double integrals in one. Okay, so you see, I just take it that this is these kind of problems, you have to work them out step by step. You know, you have to work them out, and then eventually you get to what your variables of integration are going to be. But you start out trying to just, you know, form an action plan, so to speak. Well, I have my action plan now. I have my action plan. You know, I want to get the right answer, right? Okay, I'm an engineer. I want to get the right answer because that's important, you know, right? If people get right answers, then buildings won't fall, right? Okay. Of course, in that situation in Florida, there were other problems going on, you know. But the point is, you know, you know what I'm trying to say. That's right, Charles. That's right. But you know, one thing the engineers should have done in Florida, I don't know if they can do it. Well, probably can't do it. But being that garage was open at the bottom, it lets a lot of corrosion and stuff in, you know. But maybe because it's Florida and there's flooding, I don't know, maybe they can't do it. But at any rate, I won't digress here. The point is, this is important, right? This is important. So I'm gonna use polar coordinates. So now I'm down to here, and now it's just an integration problem. Now, of course, with the circle of radius square root of 1 over, circle of radius 1 over square root of 2, my limits are radius are going to go from 0 to 1 over root 2, and theta is going to go from 0 to 2 pi. Okay. I'm going to distribute the r here. Okay. Let you keep copying here. I think that you know that building in Florida. I mean, we'll find out eventually. They'll have a report what happened eventually, and you know maybe the design was good of the building. You know, I'm not saying that it was an engineering problem, but definitely I agree with Charles. It's an upkeep problem. But you know, there have been instances where because engineers don't design something right, that people you know get hurt. You know, like if a balcony falls on another balcony, if it's not designed right, that kind of thing. You know, so okay. Oh man, Charles, the Tacoma Narrows Bridge. Yes, yes, yes. I'll have to bring that video up. An excellent example. Okay, so now what's going on here? I have a double integral, and now I'm writing the double integral as a product of two integrals. What's going on with that? How could I do that? How can I write the double integral? Good, good, excellent, excellent. That's right. That's right, Charles. This inner integral here is a number, right? This inner integral here is a number. There's no theta in there. So it's a value. It's some number, right? So numbers I can bring out in front of the integral. And so I get this. And this is a nice trick that you can use sometimes. Okay, may I go to the next page? Okay. Okay, well, we'll go to the next page here. So now I have the product of these two integrals. The second integral is easy to do. The first integral, well, okay, it's really just, it's calculus 2. I'm going to take the integral of the difference and write it as the difference of the two integrals. And so the first integral I'm going to do substitution on. I'm going to let u equals 1 minus r squared. And okay, so I'm really trying to show my steps here, trying to show the work carefully. Because you need to be able to do this as well on your third exam. You need to be able to do this integration. You know, it'll be part of the work you submit to me naturally. And I want things to go as smoothly as possible for you, okay? I know this is not easy, okay, but it doesn't have to be hard either. You know what I'm saying? Okay, so the negative 1/2 I bring out in front of the integral. I got my new limits, a half and 1. And then I put in 1 over root 2 here and 0 here. Webber sign will not want a decimal, so I'm being exact, right? All right. Let me know when you're ready and we'll move to the next page. Okay. All right, Charles. All right, Ian. All right, Ellie. All right, Madeline. All right, Juliana. Excellent. Well, here we go. Very good. So we continue on here. And I just am making an effort to get an answer in simplified radical form here. So, of course, I want to mention here, let me go. So u to the half, the antiderivative of u to the half is 2/3 u to the 3/2. And my answer in the end is going to be 2 pi times 1/3 minus 1 over 3 root 2. Now I'm going to have a question for you here. I'll let you keep copying. Kino, are you there? All right. Marwan? Okay, Marwan, all right. So I have a question for you. Okay, Gunu, good, good. Let's say on exam 3, you do a problem like this, and you get an answer like this. How do you know that answer would be wrong? 2 pi times, so the correct answer, right? The correct answer for the volume is 2 pi times 1/3, well, 2 pi times the quantity 1/3 minus 1 over 3 root 2. But let's say, you got the volume here. Let's say you got the volume 2 pi times quantity 1 over 3 root 2 minus 1/3. How would you know that answer is wrong? Okay, excellent now, Ellie. Wow, I thought it'd take you a little more time to figure that out. Yeah, this volume here is negative volume. The ice cream cone can't have the negative volume, right? You gotta have positive volume. So that's just a kind of a little thing to help, that's helpful. How many think this is pretty cool, what you're able to do here in finding these volumes? I mean, that's like the exact volume of the ice cream cone, right? In business, I think businesses would want to know the exact volume of the ice cream that they're using in the cone, right? So how many think this is interesting? Let's put it that way, interesting. Finding these volumes, these double integrals. I was hoping I'd get a few maybe thumbs up. Of course, I can't force you, but surely somebody likes this, right? Hopefully you all do. How many of you are a little bit, okay, it's a step. All right, Charles, it's a step to get there. I know what you mean. So, all right, class, I want to say one thing here, and I know it's 9:40 here, so all right, I'm going to, of course, activate everything so you can see everything. Let me stop the recording here.